Unlike Bernardinelli Bernstein, certain celestial objects will get much closer to us, and a lot sooner. One of such space guests is a killer asteroid that will fly by within less than 0.07 AU. In just about a year, a binary asteroid named Didymos, accompanied by the smaller Didymoon, will make a near-Earth approach. The bigger asteroid is roughly 780 meters in diameter, while the smaller one is just about 160 meters. However, that's more than enough to make a crater that's 6 miles wide and demolish entire cities. Even space rocks that are 500 feet wide are capable of exploding with the energy equal to a nuclear bomb. A meteor, a tiny piece of an asteroid or a comet that exploded over Chelyabinsk, Russia, created a massive shockwave. As a result, tons of buildings were damaged and roughly 1,500 people were injured. And it was only about 65 feet wide. But data concerning asteroid impacts has become even more disturbing. NASA has recently conducted an experiment that proved we wouldn't be able to do anything about an asteroid heading straight towards us, even if we had 6 months warning. The simulation of the hypothetical scenario involved an asteroid at a distance of 35 million miles. Throughout each phase of the exercise that lasted a week, scientists received more and more data about the asteroid. They found out about the object's course, odds of hitting our planet, and its size, but they couldn't come up with a working solution to deflect it. Turns out we haven't yet invented spacecraft that could eliminate such a threat within 6 months. In fact, such a mission would take us 5 to 10 years. In the simulation, the asteroid would have landed on Eastern Europe. In fact, the only way to escape the big rock was to evacuate the impact area. And that's not helping us too much. But as we know, some things that don't work out in theory can show us good results in practice. So now, NASA plans to smash a spacecraft about the size of a refrigerator into the smaller Didymoon asteroid that was mentioned earlier. The mission is called Double Asteroid Redirection Test, or DART. The idea is to take this half-ton spacecraft and crash it into Didymoon around 4 miles per second. The launch will take place sometime between November the 24th, 2021 and February 15th, 2022. However, the collision should happen between September and October 2022. This is going to be the very first test using the kinetic impactor technique to alter an asteroid's trajectory and speed, and will be a kind of military training in terms of space. Now, Didymos doesn't threaten Earth yet, but NASA's database contains more than 2,000 potentially hazardous asteroids that can get as close to us as 0.05 astronomical units. Asteroids and comets are often hard to detect, even with the most advanced technology. But at times, people equipped with homemade telescopes make huge discoveries. Just 2 years ago, an amateur astronomer named Gennady Borisov stumbled across a celestial object with a peculiar trajectory. Turns out he found a comet, and not an ordinary one either. It was later discovered by scientists that 2I Borisov is a rogue comet. This is because this type of comet has no steady orbit and will freely float through space until affected by another celestial object. As astronomers continued to study 2I Borisov, they used NASA's Hubble Space Telescope and Atacama Large Millimeter Array, ALMA, to figure out the comet's extraordinary composition. It had an abundance of carbon monoxide they didn't expect to see. And knowing about this high concentration of carbon monoxide, scientists made assumptions about its origin. So far, astronomers have come to the conclusion it should have been created in a place overflowing with CO ice. Such an abundance of CO ice is only present in space regions with a temperature below minus 420 degrees Fahrenheit. There are 2 theories about how the comet formed. It could have been born around a red dwarf, a relatively small star with a low surface temperature. Otherwise, it could be a tiny fragment of a dwarf planet. This has become the first comet that entered our solar system from a place outside of our star's influence. But this is not the only thing that captured astronomers' attention. When approaching a star, a comet's particles start to melt and generate a fuzzy cloud around its nucleus. This cloud is called a coma. So what scientists noticed was a unique polarization in Borisov's dust grains. Now, polarization is the direction light waves ripple in space. The higher the polarization, the more focused the light is in a single direction. That's exactly what 2I Borisov's coma demonstrated. In the scientific community, this was a big deal. Similar to the way our skin reacts to direct sunlight, the more a comet interacts with a star, the bigger the impact on its materials. Eventually, the polarization of the comet's coma gets reduced. But what we see with Borisov's comet is quite the opposite. This can only mean one thing. It is rarely or never bathed in a star's light, radiation, or winds. So it's one of the most untouched and well-preserved comets we've ever detected. This leads us to the conclusion that the comet contains unaltered information about the materials that formed it in the first place, which could have happened some thousands, millions, or even billions of years ago. And since astronomers believe the birthplace of 2I Borisov partially resembles our solar system, that comet can reveal valuable information about another solar system much like ours. Borisov's comet already traveled past our Sun in 2019. But this doesn't mean there aren't any other celestial objects about to visit us. We can only hope our telescopes will look in the right direction and at the right time so that we can prepare ourselves once they show up. We live on a perfectly functioning planet, but don't even think about how fragile our world is. Should you change one element and the entire system stops properly operating, the life that we're so used to would no longer be the same. If this happens, most living organisms on our planet would disappear. And all this is possible if our blue dot just stops spinning. But is this even possible? What would happen exactly? And how could this threaten humanity as a species? The Earth makes a revolution around the Sun once every year, or once in every 365.2425 days. But also, our planet rotates around its axis, making one revolution in 23 hours, 56 minutes, and 4 seconds. Let's start with the rotation around our star. Stopping this rotation would mean a definite death for all mankind. It's the force that keeps the Earth in orbit and holds back the mighty gravity of our star to keep us from falling into it. This is similar to how speed keeps a circus motorcyclist driving on the walls from falling. And if a driver hits the brakes, he would crash right down. So, in case our planet stops rotating, it would also rush towards the Sun. After a while, it would fall into the fiery ocean of the burning plasma. Just in a matter of seconds, Earth would evaporate and disintegrate into atoms. But how could this happen? The most painless scenario for us is an instant stop of rotation. The Earth revolves around the Sun at an orbital speed of around 107 kilometers per hour and travels at a distance of 2.6 million kilometers a day. So if our planet's rotation stops within a second, the Earth would experience an overload of more than 3000 G. Everything would instantly be destroyed and turned into dust. Suddenly, human beings would achieve a speed of 107,000 kilometers per hour, or almost 30 kilometers per second. The first cosmic velocity, or the speed at which the body becomes a satellite of our planet and does not fall on it, is roughly 7.9 kilometers per second. At that speed, unless you bump into something along the way, you become an astronaut and find yourself in orbit. But that's just the first cosmic velocity. The second cosmic velocity, or escape velocity, is 11.2 kilometers per second. At this speed, the body leaves the Earth forever. This is the speed that the Apollo spacecraft had to gain to reach the Moon. This fast, we'd all travel into the depths of space and revolve around the Sun in the form of space debris. The planet itself would not survive. Under the influence of such a monstrous overload, Earth would break into many pieces. Its core would be exposed and its magma would splash out right into the cosmos. The spectacle would be quite bewitching in its horror, but there'd be nobody to witness it. Still, this is the best scenario for us. What could be even worse? It would be a lot worse if the slowdown happens smoothly, without fatal overloads for the human body. In this case, the planet would rush towards the Sun along the ballistic curve. It would be reminiscent of a spacecraft deorbiting. As we approach our star, the temperature on the planet will constantly rise. At first, it would be hot, then very hot. Finally, it'll become unbearable. At a distance of about 70 million kilometers from the Sun, the temperature on the Earth's surface would exceed 212 Fahrenheit, but that's just the beginning. people that would stay in underground bunkers equipped with cooling systems would last the longest. But when the temperatures rise to 1,000 degrees, nobody would survive. Because of the enormous force of gravity at a distance of a couple of million kilometers from the Sun, our planet would be torn to pieces and collapse into a fiery ocean. Our star would become a global crematorium. This is the finale that awaits mankind if the Earth stops rotating around the Sun. But what would happen if our home stops rotating around its axis instead? If this happens quick enough, the results would be somewhat similar. Even though things wouldn't probably be turned into fine dust, they'd still be broken apart into fragments. At the equator, Earth's rotation speed is about 1,670 kilometers per hour, so the overload would be approximately 47 G. And as you go deeper or move towards the poles, the overload would increase. The planet itself is unlikely to collapse, but multiple earthquakes would occur in many parts of the world. For the Earth, such an event would be felt as a blow of a monstrous force. Because 1,670 kilometers per hour is only 0.46 kilometers per second, you wouldn't fly into orbit. At this speed, you'd be thrown along the course of the Earth's rotation in a western direction, and it's highly unlikely anyone would survive the landing. People who live closer to the North Pole, scientists in Antarctica and the Arctic would have the best chance of survival. No building can withstand 47 G, well, except for perhaps the Antarctic and Arctic stations where overloads wouldn't be so intense. In addition to earthquakes, severe tsunamis would take place all across the globe. This would be a lot more terrible than shown by any blockbuster. After all, the entire world ocean would begin to move. This is 1,338,000,000 cubic kilometers of water. There would be kilometer-high waves, so it's unlikely that even humans being close to the poles could survive. People on airplanes, the moment the Earth stops, would not survive either. All planes that were flying from east to west would sharply rush forward with an acceleration of 47 G, burst and crumble from such an overload. And planes that flew in a different direction would be dragged sharply to the west, either sideways or tail first, but all with the same outcome, almost an instantaneous destruction. The only way humanity would have a chance of survival is if the deceleration of the Earth's rotation is slow. At a certain value of the deceleration, the friction force will even hold a person still instead of throwing it like a stone out of a catapult. If this is the case, many buildings would survive, and tsunamis wouldn't cause a global catastrophe. But as the dust from the destruction of some buildings settles, people thrown by a sharp push would rise from the ground. And it would then be the question of how to survive on a planet that isn't rotating. Stopping the Earth's orbital rotation is just an abstract assumption, but a gradual slowdown in the rotation of the planet around its axis is not just possible, it's happening right now. The Earth is constantly slowing down, and our days are becoming longer. Eventually, such a slowdown can result in a single Earth day lasting as long as one Earth year lasts today. That would mean a complete stop of rotation. Similar to the way our moon faces the Earth, our planet would have one side always facing the Sun. We were only able to see the moon's reverse side on October the 7th, 1959, when the Soviet Luna 3 station photographed it. So, why is the rotation of our planet slowing down? The reason is tidal forces arising from the gravitational influence of one celestial body on another. One example of tidal forces is the ebbs and flows caused by the rotation of the moon around the Earth. Under our satellite's gravitational influence, the points on the surface of our planet that are closer to the satellite are attracted stronger. As a result, there's deformation that can be easily spotted on the surface of the water. This is because, unlike solids, water molecules are less connected to each other. As the moon pulls on different parts of the Earth, our planet's water bulges out on the side closest to our satellite and the side furthest from it. On a planetary scale, these forces may seem insignificant, but this isn't the case. There's a narrow and long bay in the Sea of Okhotsk, Russia. It's called Penzina Bay. The height of the tides there reaches 9 meters, and if the Earth, the Moon, and the Sun line up in a row, they grow to 12.9 meters high. These are the so-called spring tides. It's been calculated that if a power plant operating on the energy of these tides is built, its capacity would be 120 gigawatts. To compare, the United States has a total hydropower capacity of about 80 gigawatts, which is 1.5 times less. Such a power plant would be able to produce 1,054 terawatt-hours of energy per year, and all that would come from a single place on Earth. So where does this gigantic amount of energy from tidal forces go? Friction. Waves on our planet rise, fall, and beat against the shore. Now imagine a ball rotating on its axis that rubs against a wall. What happens to its rotation? It slows down. In the same way, Earth is gradually slowing down its rotation. Also, there are tides caused by the attraction of the Sun. Our star pulls the Earth 400 times stronger than the Moon. But the difference in the force of attraction between the surface of the ocean and at its bottom is less when it comes to the Sun. As a result, it creates weaker tidal forces, but they still exist. Every 100 years, a day on Earth lengthens by 1.5 to 2 milliseconds. In 200 million years, a full day will be 25 hours long. In 5 to 6 billion years, the Earth's rotation around the Sun and its own axis will match. Under such circumstances, the effect of the tidal forces would be minimal. This is because every system in the universe aims at achieving an absolute minimum of energy. The Earth has synchronized with the Moon in the same way, and it's not just our planet. All the satellites of the planets that are relatively close to them, like those near Mars, Saturn, or Jupiter, are synchronized. Our Sun has already synchronized Mercury. The same will happen to the Earth in about 5 to 6 billion years. And when it happens, there'll be a permanent day side and a night side on our planet. Those who temporarily reside in the Arctic Circle already experience a night for half of the year and then a day for the rest of the year, and they manage to operate just fine. But it's only a relatively small area of our planet. So what if this happens on a global scale? The heat balance of the planet will change. Strong winds would start blowing from the sunny, hotter half to the dark and colder half of the planet. On the night side, flora will have a very difficult time. Many plant species will perish. Only species that can exist with a minimum amount of light and heat would survive. Entire fields of wheat and other agricultural plants would be gone. There would be some moss and mold left. The same will happen with fauna. But you can't survive on moss and mold only. So at least for the several upcoming years, there will be hunger. But even this is not the worst. When the Earth rotates, centrifugal forces flatten it at the poles and create a hump at the equator. The diameter of the planet there is about 43 kilometers larger than it is at the poles. Without rotation, the hump would disappear and the oceans would float towards the poles. The Earth would have one giant continent and 2 oceans: Antarctica, Greenland, Canada, Siberia, entire Europe, a part of China, and half of New Zealand would go underwater. Along the equator, up to 30 degrees north and south latitude, plains and mountain ranges would appear. This would be a real disaster, with millions of victims. And even this is not the worst. As the Earth would significantly slow down its rotation from 24 hours to 365 days per revolution, its magnetic field, consisting mainly of liquid iron, would decrease as well. Flows would be formed in the Earth's core. They would rub against each other and become electrified, forming loop currents. As a result, a system of currents would circulate along a conducting circuit which would induce a magnetic field that encircles our planet. The northern lights are a visible result of this process. We could easily live without the magnificent northern lights, but not without the protection against solar radiation. Our magnetic field, weakened by 365 times, wouldn't save us. So those lucky enough to escape being covered by tsunamis, flooded during the formation of new oceans and continents, and those surviving the hunger, would still have to live inside underground caves where radiation cannot reach. Still, even inside caves, there wouldn't be many places suitable for survival. People would only be able to live in tiny areas on the border between day and night sides. Depending on the hemisphere, there'd be eternal dawn or sunset. And it wouldn't be possible for all human beings to settle down along the entire favorable line. This is because a large part of the land would be flooded with oceans, and you'd have to choose an area with an optimal atmospheric pressure and temperature. Our descendants would probably know for sure whether life is possible on a planet that's always facing its star on one side.